Each year, mechanical engineering students at the University of Warwick take part in an industry design challenge. Working collaboratively with peers and industry professionals, they apply their learning to innovate on mechanical projects such as all-terrain vehicles and power delivery systems. This year's task, to design a multi-cylinder two-stroke internal combustion engine using components from an existing single-cylinder unit. The first obstacle was to decide on the use case of the engine. Dating back to 1872, internal combustion engines have long been a crucial power unit in many engineering sectors, most notably automotive. We wanted our chosen application to be realistic within the project scope, but also challenging and engaging. Auto racing was deemed the perfect balance. This high-performance setting enables the exploration of state-of-the-art materials and manufacturing techniques, while removing limitations such as cost and maintenance schedules. Inspiration can be gathered from existing concepts within motorsport, and both the Formula Series and the World Rally Series provide direction towards each of the design's iterations. So where did we begin? Serving as a starting point, a single-cylinder engine was provided for examination. Measurements were taken using precision tools, vernier calipers, bore gauges, and micrometers. Basic CAD models of all the initial components were provided, with only the engine block and crankshaft having to be designed from scratch. Next came choosing our engine configuration. To refine our layout options from the vast array of potential configurations, a multi-criterion weighted Pew matrix was used. This compares each option's perceived performance based on a variety of parameters, with the inline 3 being selected as the base unit. A V6 was ultimately chosen, which excelled due to the high power possible, the perceived wow factor, and the ability to access marks due to the complexity of the design. A failure modes and effects analysis, or FMEA, was conducted on various aspects of the initial engine. This aimed to identify potential improvement areas that we may wish to develop within our design. The detection, severity, and occurrence numbers were selected in the context of a high-performance racing use case, with the cylinder found to be the component with the highest risk priority number. With 6 cylinders required, duplication and layout of the provided CAD was a useful visualization step. Pistons were assembled onto a single crankshaft, and both 60 and 90 degree bank angles were considered. The former is industry standard for its balance and compactness, but the latter, used in Formula 1, allows for better thermal dissipation. The ideal layout for balancing is 120 degrees, but it would be an incredibly wide engine. Then came the first of 2 opportunities to show our engine to an industry professional, Gurinder from Meggitt. The first meeting brought to light the importance of the bank angle in heat dissipation, with a wider angle cooling better. Heeding his advice, we developed a 90-degree format. This choice led to the design of the first engine block, which was a bulky piece of steel simply holding the components in their relative positions. The pistons were staggered with enough separation to allow for independent crankcases, with baffles to ensure that each cylinder would be allocated an even fuel charge and develop enough pressure difference to properly breathe. The staggered pistons made this engine block long and slender, a difficult shape to put in a car. The solution? To split the crankshaft in 2. With separate crankshafts, each cylinder has its own crankcase, allowing independent breathing and full flexibility of firing order. This reduced the engine block length by almost half, and the engine footprint was further reduced by reverting the bank angle to 60 degrees, as the split crankshaft separated the banks, avoiding part collision and improving cooling. Looking at the manufacturability of the proposed concept, we realised that to build and assemble the product, some form of access to interior faces would be required. So, the engine block was split horizontally at the crankshafts to allow the assembled shafts to be dropped into place. This required consideration of 2-piece bearings, gaskets, and mechanical fastenings, but results in a realistic and strong model. Chamfered dowel pins are used to align the 2 halves, and the main bearings are split to sit around the crankshaft. At our second meeting in April, Gurinder was impressed with the progress our engine had made and highlighted the importance of creating a story within the report. With the seal of approval from an industry professional, the design was soon finalised. A compact 6-cylinder, dual crankshaft, 60-degree bank angle, 2-stroke performance engine. These crankshafts are housed in split main bearings, custom-made trimetallic journals finished with high-performance P-Max black, low-friction, high-wear resistance coating. Each bearing has a circumferential oil groove, and all lower bearings have a hole for the ingress of lubricating oil, which is carried up through the lower engine block. The crankshafts utilise straight-shot lubrication to carry oil in a straight line from the main journal grooves to the crank pins. The oil is pushed out towards the crank pin by centripetal force of the crankshaft rotation. The central four bearings also have thrust bearings, flat trimetallic contact surfaces, again coated in P-Max black, recessed into the engine block and butted up against flanges on the crankshaft, preventing any lateral movement. The two crankshafts are coupled together with a toothed Kevlar belt, with its flexibility allowing for minute discrepancies between the speed of the two shafts. Belt drive is a fail-safe system. If one engine half fails catastrophically, then the belt will snap or fly off and prevent further damage to the other half. The block has 4 mounting points cast into its outer faces, and 6 apertures on the bottom for inlet valve assemblies. The upper engine block has 6 apertures for the cylinder heads. There is extra material inside the crankcase to house mounting holes for these components. The internal corners of the crankcases are filleted in order to allow finish machining with a circular mill, and overhangs are avoided where possible to minimise undercut milling operations. 6 individual head gaskets sit on top of the upper block. Separate gaskets mean that a blowout on one will not induce leakage into the others, again helping the engine to fail safely. We learned from the seminars and design reviews how critical material choice is to preventing failure under high stresses and temperatures, and how it provides an opportunity to reduce weight, cost, and simplify the manufacturing process. In crankshafts, material strength is critical to prevent failure under the high rotational and shear forces from the pistons and pressure from the cylinder case. For our crankshaft, 4140 steel is chosen. It has a high percentage of carbon and is alloyed with molybdenum for toughness, resulting in a high factor of safety. As the biggest component, the engine block provides ample opportunity for lightweighting through material choice. Aluminium 6061T6 was chosen, an alloy with high fatigue, shear and tensile strength, good workability and strength to weight ratio. We could see from the initial FMEA that cylinder wear was a potential risk. Thus, wear-resistant Alusil cylinder plating will be used to coat the cylinder walls. This is chosen in place of steel liners as it is thinner and has a similar thermal expansion coefficient to the cylinder head, limiting the effects of differential bimetallic thermal expansion and thus the chance of engine seizure at high temperatures. The engine uses state-of-the-art manufacturing methods typical of the motorsport world, such as sand printing for the engine block and hot forging for the pistons, conrods and crankshaft, with both methods followed by 5-axis CNC finish machining passes, especially on contact faces. Engines require extensive pre-production testing to prove reliability and safety. Dynamometers, or dynos for short, are a brilliant tool for determining points of failure and potential design improvements. Performance testing focuses largely on the power output, specifically its peak torque and RPM for sustained periods of time. To ensure rigorous testing of engine scenarios, we would run a predetermined input pattern cycling through a range of race representative accelerations, vibrations, fuel concentrations and thermal distributions, as well as unrealistic patterns such as cycling quickly between 0 and max revs to push the absolute limits of the engine. Sections of the engine may also be tested in isolation to evaluate limited functionality, and the unit will also be tested collectively with other components. The final engine represents a strong design for a high-performance power unit and meets the requirements outlined in the project briefing. A number of further developments would allow the concept to realise its full potential, such as wrapping the cylinder banks in liquid cooling jackets and scaling up the cylinder displacements and piston diameters. Some might argue that the world is moving away from the internal combustion engine, but with rumours that Formula 1 may move towards a two-stroke variant, and with innovations in green synthetic fuels, it is probable that ICEs will adapt as opposed to being replaced. As a team, the road to formulating the design has been long, with some members strong in CAD modelling and others in video editing, and every member having something unique to contribute. We are proud of what we have created and hope that our team dynamic and ingenuity can be seen in the quality of the work produced. Thank you for listening.